but it shouldn't be a problem. Okay, so today we'll be talking about artifacts in EEG. In reality, some of these artifacts are going to affect multiple things, not just EEG, so you might see them in MEG or ECOGs. So it's not like this is just an EEG set of problems. They might even affect FNIRS to some extent, depending on the system. But since this is an EEG-based class, these are things that I have to deal with EEG data, and these are things that you're going to have to deal with when you're recording data for the project or in future lab research. So what is an artifact? An artifact is pretty context dependent because the actual source of noise in this case, which is not the signal that you're trying to extract, could in itself be a useful signal in other contexts, and we'll talk about that. But in general, an artifact is going to be something that is not related to the signal of interest that is still being generated throughout the recording or during moments of recording that we want to get rid of. And in this case, the goal is always to increase our signal-to-noise ratio, which means that we want the power of our signal to be larger than the power of our noise. And again, I just want to emphasize that because I'm going to be talking about some of these things as artifacts, just know that all of these things by themselves are not always artifacts. You can use some of these things to get information. It just depends what the questions you're asking are. In general, we need strategy to mitigate different types of noise. And most often, we're going to try to do simple filtering to get rid of them because that's a very simple set of operations. The filter properties are typically well understood. And it works really well for a lot of different types of artifacts. But there are some that you can't just filter out. And in those cases, we have to make some decisions about what we want to do with our signals. So we either want to discard noisy segments. So for example, let's say we're doing a P300 speller and we detect some artifact in a particular epoch. We can either just say, okay, I hate that epoch, let's get rid of it, let's not analyze that data. Or we could try to do something called artifact correction, which is, okay, we kind of understand, or we really understand how this artifact is being generated and how it's affecting our signals. So let's apply some sort of mathematical approach or modeling approach to remove those artifacts but preserve our original signal. And as you might have some intuition for, the second thing is a much harder problem. So it's really easy to just say, okay, that data, it's trash, get rid of it. And a lot harder to say, okay, let's actually figure out what the trash is and extract it and preserve our signal. So before we move forward, I want to introduce you to this very popular saying. It's known as Hansen's axiom, named by John Hansen, who was at UCSD working with Steve Luck. And it's just very simply, there is no substitute for good or clean data, depending on how you want to quote it. And what this axiom gets to the heart of is that you can apply all of the fancy filtering you want and all of the fancy modeling you want, but if you did not, I did share my screen, yeah. But if you didn't collect high quality data to begin with, you are just screwed, essentially. There's nothing that you can do if your baseline data are not corrected well. So what could this mean for EEG? So it could mean that you have poor connectivity between the electrodes and the subject's scalp, right? So we'll see this with dry electrodes where they don't have as good of connectivity to the scalp because they're pushed up on top of the hair. They don't have this conductive medium of gel that's bridging the tip of that electrode to the scalp. And so because of that, our signal quality tends to be a lot worse than these gelled or wet electrodes. Now, you can apply some filters to these data and extract some meaningful signals, but at the base, the overall truth is that those dry electrode recordings are always going to be worse than the equivalent wet electrode recording, and there's no amount of magic filtering or processing you can do to change that. You just have to deal with the fact that this is as good as the data can get after you apply, your filtering or cleaning steps. And really, this is just here to make you appreciate the difficulty and the art of experimental design and data collection, which is something that is not trivial, and a lot of people who are interested in just doing data analysis tend to forget. And once you learn more about how hard it is to do this type of research, the actual data collection, you get some appreciation for good data sets that you work with, and you'll sort of maybe forgive people who have extra bad data sets, although I don't. I think people release way more bad data sets than good data sets. And it's not trivial to discern which is which unless you have experience. So if everyone followed Hanson's axiom, we'd be in a better position, but sadly that is not the case. But okay, so let's talk about some common EEG artifacts. Eye blinks. These are probably the most common artifact you'll interact with. They are very large peaks and troughs within the time series data. And in reality, they are in order of magnitude or orders of magnitude larger than the EEG signal, so they completely overshadow the EEG signal at that time. They affect pretty much every electrode, but they're mainly affecting the frontal electrodes, and it's pretty easy to detect them and relatively easy to correct for them. Now, what's interesting about blinks is that the reason we see such a large potential, and here's an example of blink data, is actually because the eyes are dipoles, which means that there's a difference in charge from the front of the eye and the back of the eye. And because of that, when the eye moves, not only if the lids blink, but also if they move just around and start looking around, you can very clearly pick up this electrical potential as it changes and changes orientation, which we'll talk about. So yeah, as we can see, here's some time series data. In the first channel is FP1, which is the closest electrode to the eye. Essentially, it's just right above the brow. And we can see there's a very strong, in this case, positive peak right at FP1. And then if we look at FZ, which is still pretty frontal, but down the midline, we still see a positive peak. And then as we look at the other electrodes, the polarity is changing, and even all the way back to T7, which is pretty far into the center of the scalp, we're still seeing the influence of the blink. So as you can imagine, and obviously all of the, well, at least I hope it's obvious, all of the EEG signals at those time points are being completely overshadowed by the magnitude of the blink. And so this is a problem. We typically want to deal with this. And again, this is a case where I'll say that a blink is not necessarily always a noise. So when I pitched that hypothetical project that the TAs and I would work on, we said that we would use a double blink detection as a control signal. And that might make sense because humans don't often blink twice in rapid succession. So if you detect a double blink, which again, if you look at these signals, should be pretty easy to do, it makes sense to use it as a control signal because it's reliable, a user can generate it consciously, So again, artifacts are not always just noise, they can be useful. So how would we go about detecting or rejecting these blinks? There's a very simple algorithm called simple voltage thresholding. It's so simple, it needs simple in its name. And you typically will do this after you baseline correct or DC offset correct your data. And all you're doing is you're taking, in this example code, you literally just compute whether or not the minimum point is lower than some threshold or the maximum point is higher than some threshold. You could also consider having different thresholds for positive and negative if you have some reason to expect that, or you could take the absolute value of your data. But in this case, this is a very naive and trivial way of thresholding. It works surprisingly well for blinks. So since something like this is so easy to implement, I have this implemented in my real-time BCIs, and it's therefore possible for me to detect in real time whether or not somebody has blinked during a trial. This is very useful because, for example, I have this criterion where I want to make sure that I'm getting 30 good trials of a certain data type from my participants. And in this case, good means that it's free from artifacts. Now, I can't guarantee with simple voltage thresholding that I'm excluding all artifacts, but I can be very confident by just setting a single value that I'll be rejecting and detecting every single blink because they're just giant. I mean, Yeah. You can't even see the peak of this first one because it goes off screen. It's so big. So setting the actual threshold it can be difficult. Typically, you want to do this subject by subject. So what you can do is at the start of an experiment, you can have the subject blink a few times and record what the threshold is. Now you have to be careful because when you tell a participant to voluntarily blink, the values, like the amplitude of those blinks, are going to be larger than when you just detect regular blinks. But you could mitigate that by just having a 1 or 2 minute period where you just tell the person to, hey, we're going to record some resting EEG. Just look at this fixation cross for a minute, and then you can just use the activity from those blinks as thresholding, and you could do that automatically as well. But yeah, I've used values of 150 microvolts in general. That seems to work, but you might need to fine tune it for some people. And there are variations on simple voltage thresholding that can be used more effectively. So for example, rather than looking for the maximum value on all channels, you could just use a subset of channels to make the calculation slightly faster. You could also use smaller windows, so you don't necessarily need to use the entirety of the epoch. You could say, okay, if a blink exists at this time, it's super critical, but if it exists maybe towards the end, it doesn't really matter, and we'll just explain that in our epoch, or we'll shorten the window that we're plotting to show people like, hey, the blinks don't matter. You could also use something called moving window peak to peak, which is similar to simple voltage thresholding, except it's essentially trying to take the time points, either the maximum and minimum or two neighboring time points, and looking to see is the change in time point from point A to point B larger than a certain threshold, and then you can reject it like that. So this is just the groundwork. It's a very simple algorithm. It works by itself unbelievably well. I remember, this is anecdotal, but when I was at my old lab at SDSU, we were recording this multi-100 person study, and we had something like 400 subjects recorded already, and we have an automated artifact rejection pipeline that we used that was actually given to us by Emily Kappeman, who comes from Steve Luck's lab. And we have, I think, 6 or 7 different ways of flagging different artifacts. And the one that caught most artifacts, so simple voltage thresholding was the most effective, and it also caught a lot of artifacts that the other artifact detection methods caught. So we'll talk about a step function later for detecting lateralized eye movements, but I think I found 0 instances across all 200, 400 subjects, I can't remember how many at this point. There was no case where a different detection algorithm detected something that simple voltage thresholding didn't also detect. So it just worked the best out of everything else, which was surprising. And we still ended up flagging all of the other ones, but yes, they were all redundant because simple voltage thresholding was so good. Now, to be fair, this is true because we're very careful with our data collection, so we make sure that we set things up in such a way that we're not going to be getting a lot of artifacts, so the fact that most of them are just detected by SVT is not surprising. So, your results may vary. And then how would we go about actually correcting these eye blinks? There are honestly probably hundreds of papers talking about different ways to do this. One of the most popular is the Graton method. And essentially what this boils down to is using dedicated channels for collecting eye movements and blinks. What we call these EOGs, electrooculograms. And if you see on my face, I have 2 electrodes that are on either side of my face. These are called our horizontal EOGs or HEOGs. And then I have 2 electrodes that are above and below one of my eyes. These are our vertical EOGs or VEOGs. And then I just have a ground electrode. But you don't necessarily need that ground if you're using electrodes that are connected to your main amplifier. In this case, we're using auxiliary EOGs, but don't worry about that. And for eye blinks, you don't need the horizontal ones. All you need is the vertical ones, and you can really accurately pick up these blinks. And then you can say, okay, we know what these blink signals look like. Let's subtract that out from the rest of our signal using this regression-based approach. It works quite well, but what you have to understand is that whenever you're doing a subtraction approach like this, you end up throwing out some of your data, even though you end up removing most of your noise. So although the EOG electrodes are picking up predominantly EOG data, this eye blink data or eye movement data, they do contain a tiny amount, a non-insignificant though, amount of EEG data as well. So when you apply the subtraction method, yes, you're trying to remove this artifactual signal, but you also will be removing some of your data. So correction always has to be, you always have to think very carefully about whether or not the approach that you're using is good enough or appropriate enough given the set of artifacts and given the circumstances that you're trying to analyze the data in. And you can't just willy-nilly say, okay, yes, we have artifacts, we're going to use this method to get rid of them. It's not that simple, even though some experimenters might make it seem like that because they don't understand their signal processing methods well enough, and some data analysts might say it's that simple because they don't understand their data well enough. So just be very careful, be very conservative, understand your data before trying to remove artifacts. And then let's also, so in general for all these things, I'm going to talk about how they look like, the detection and rejection, the correction, and also sort of the Hansen's axiom for this thing. What can you do before you even collect the data to make sure that you're going to be reducing these artifacts? So one thing is if your subject wears contact lenses, have them wear glasses instead. In general, though, it should be noted that participants who wear glasses tend to blink more than people who don't wear glasses anyway. You can also explain to subjects that they can blink normally and that you'll monitor, and you'll say something if they're blinking too much. So this was actually in all of our protocols at my old lab, and I still use it to this day. You'll just, there's this whole script that you tell subjects about what to do, and actually, before we start recording, we'll actually show the subjects the raw EEG data as it's coming in real time, and we'll tell them, okay, go ahead and blink once for me, and they'll blink, and you see this massive thing, and even though the subjects are not trained to collect EEG, even though they don't necessarily understand what's being shown to them, it is very obvious to them when they see the blink that, okay, wow, that is a huge signal. And even children are very receptive to this, and you can tell them, okay, yeah, you see that? That's really bad, we don't want that. And they're like, okay, yeah, for sure. And what you want to do is you want to design experiments that have either ideal times for blinks, so you can tell them, hey, when you can't blink if once you're seeing these stimuli. Well, you don't want to tell them you can't blink. This is something you'd tell them if you need to give them feedback. But you would say, hey, please blink normally. An ideal time for blinking would be during the fixation cross. And then you'd only go in and tell the participant, okay, hey, you're blinking too much if you need to, because you don't want to give the subject an additional task, if that makes sense. So we're thinking about them completing an experiment like a P300 speller or, an N400 language task. You really want the user to be focused on the task at hand, whatever you've given them, and you don't want them to be thinking about not blinking or blinking at specific times. So this is really, you want to give participants this feedback only when you need to. It's really important in general to design relatively short blocks that have frequent breaks. So this means that, okay, I want to get, 300 trials of this data set, but you don't want to just have the participants sitting there and seeing 300 trials one after another for like 15 minutes. That would be horrible. What you want to do is you want to chunk these things up into what we call blocks of a certain number of trials. So, we take that 300 and we divide it into 10 blocks of 30 trials. Let's say that those trials are about 1 to 2 minutes long. At the end of that 1 or 2 minute long trial, then you say, okay, you're going to have this break period every 1 or 2 minutes. At this thing, feel free to move around a little bit. If you feel like you're sagging, blink, take a drink of water, whatever you need to feel comfortable, and then start the next block when you're ready to go. Typically what we'll do is we'll have shorter breaks that are timed. So, okay, this is going to be a 10-second break, and then every, let's say, 3 blocks, 4 blocks, then you give them a self-paced break, as we call it. And you'll know when an experiment is designed like this because you'll read it in the methods paper that they'll say, okay, yeah, we have them X minute break or whatever, second break, and then they have a self-paced break every X blocks or X time or something. One sec. And it's important as an experimenter, while you're collecting the data, to monitor the participants. So what you'll be doing is you'll be, depending on your setup, you should at least have access to the real-time EEG coming in so that you can see how the signals are looking. And again, blinks are so easy to detect that you can just see this coming in real time and monitor how often the participant is blinking. Typically in acquisition software, you can also see when certain events are happening. So for example, sometimes you'll see a participant is consistently blinking right after they've seen a certain stimulus. And that is something that you particularly want to control, because one reason artifacts are a problem is they can become confounds to your data collection. So let's say you have a specific type of stimulus that is consistently causing participants to do something like blink, and another type of stimulus is not, and you are not aware of this, you're being a lazy experimenter, you didn't look at your data afterwards, and you just calculate the grand average ERPs and you say, wow, when people see scary images, there's this massive positive deflection that's like the biggest ERP we've ever seen in the world, a couple hundred milliseconds after the stimulus comes up. And that might be true. There might actually be some neural signal that is generating that, but you could also just be recording something like a blink, and somebody sees something scary and they instinctively get startled and they blink. So you want to be very careful with, it might not be clear why these artifacts are such a problem, but it's because they can lead to false claims about something that is actually just noise. And it's better, in the case of artifacts that are consistent across both trials, and if they're somewhat random, they can average out over time. So those aren't as big of a problem. But when it's something that's systematic and it's a confound for a particular class or set of classes, that's when you run into very dangerous territory and you need to be extra careful. Okay, any questions about blinks? It's a very common one. Okay, cool. Oh, yeah.
Can you go over the rationale of having people wear contacts, or if people wear contacts, having them wear glasses?
So this is something that Steve Luck says.
Usually I would have it the opposite.
Yeah, well, so typically glasses can be a problem when you're recording EEG because the bars of the glasses have to go somewhere, right? When the participant has a cap on, they have electrodes, some of them are on the temple where the glasses are going to sit. And so typically you'll have the participants take their glasses off, you'll cap them, Velcro, whatever, and then we'll place the glasses back on. Now sometimes the way that the person's head is arranged and where their ears are and stuff, the glasses don't interact and they don't touch any of the electrodes and you're fine. Sometimes the electrodes are going to be resting on top of electrodes, or in the worst case, because their frames are uneven, they'll be resting on one electrode on, let's say T7, but they're not resting on T8, which is in the equivalent other side of the head. And that can lead to artifacts by the glasses moving when it might cause T7 to look slightly worse than T8, whatever. Is that why you would normally have participants wear?
That is the biggest reason, but also sometimes I'm just paranoid that there's some kind of metal in them or something that would be problematic with recording.
Yeah, I think the metal is less of a problem, but most glasses are plastic nowadays anyway. But yeah, the logic that Luck provides, and I'm inclined to, I don't tell my participants either way. I just say, okay, if you wear contacts or glasses, wear contacts or glasses, because in general, these participants do tend to blink more anyway. That's something that you notice as well when you're just recording from people wearing glasses and contacts. I had a research assistant that wore glasses, and the reason I added my automatic artifact detection was because of him. Because when I would collect data from him, he just could not stop blinking. I mean, during the online phase of the BCI, he was just blinking nonstop, and it's like, okay, I need some system to detect these blinks so that I can make sure I'm recording 30 good trials from him. And I set this cutoff where it's like, okay, the maximum number of trials I'll record is 60, which means you can record 30 bad trials and 30 good trials before I'm like, okay, or 30 bad trials maximum before it's like, okay, this is too bad. And he's the only subject I've ever had that consistently had to reach that limit. But that general trend is true. So glasses wearers tend to blink more. But I think what Luck's logic here is that contacts can irritate the eye and dry the eye out, and that having no contacts in is going to be slightly less irritating and less of a problem than having glasses in hand. They even suggest having Eye drops handy, although this is something that you probably don't want to give participants if they don't typically use eye drops, and it would be better instead if you think that you're going to have a very rapid-paced visual, task or something, to tell participants, hey, bring your glasses if you have them, and also if you wear or use contacts, then consider bringing your glasses and your contacts and eye drops and whatever. You can get very broad with what you tell participants to come in with. Does that?
For eye tracking. Eye tracking is the other reason.
Yeah. Yeah. So eye tracking is problematic with glasses. The reflections can mess up what the video camera is recording, which is a pitch for why you would want to use EOG-based eye tracking instead. But yeah. So can artifacts be generated by people intentionally trying to stop blinking? The short answer, so are you thinking of a situation where somebody is just doing like a staring contest essentially, where they're just like holding their eyes? Yes. So that does happen, and you'll see that as higher frequency muscle noise in the electrodes from the forehead up. So like FP1 and FP2, you'll start seeing these very high frequency muscle signals if participants start off like calm and then trying to keep their eyes open, really expand their eyes out. So that is why we give them the instruction at the beginning of the experiment that, hey, you should blink normally. We'll let you know that if you're blinking too often or something. It's because you don't want to put them in that situation. Yeah.
So what if they're not trying to hold their eyes open, but they're just consciously thinking about their blinks?
Yeah, so if they're not consciously trying to so they're consciously thinking about not blinking, but they're not doing the crazy eye thing, that can add a potential additional layer of a task concern. However, similar to if you have this random variation due to an artifact across all signals, if the person is constantly thinking about don't do this across the entirety of the task, it shouldn't disproportionately affect a class, and then when you compute the averages of the signals, or if you're doing difference waves, it should cancel out any potential concentration on blink-related effect. But there is a non-zero chance, and we know from lots of ERP literature that the more tasks people have, the different their certain ERP components are in certain situations. So ideally, you don't have participants in that situation, but that would be less bad than somebody, well, depends on the context, but would be hopefully less bad than somebody who's constantly blinking, and you have to deal with that. Yeah, good questions. Okay, another very common source of noise, and we sort of alluded to this with the crazy eyes, are muscle artifacts. These tend to be mostly from the neck and face muscles, which are, the neck muscles in particular are unbelievably powerful. And especially if you have a participant who is sitting improperly in a chair, like if they're slouching forwards or backwards, their neck can be activated in such a way that it produces these really powerful high frequency spikes. And you can just see this in electrodes. And also I'll show a figure of this, but there are muscles that go all the way up to the temples, and the electrodes T7 and T8 really pick up those muscles super well, to the point where there are a lot of montages that just get rid of those channels and put them somewhere else because they just record muscle noise most of the time. They tend to be localized in higher frequencies, typically 30 to 100 hertz is where you'll see a lot of those muscle signals. And they're relatively easy to detect and reject, but they can be difficult to correct for. So here is an example of I just loaded up a random data set that I had and plotted it. This is just after high-pass filtering. So this is just the raw EEG data at a certain point for 64 channels. And we can see that, data are looking pretty good, pretty clean, whatever. And the participant is completing the task. And then right after this last marker, which is that green bar, the experiment is going to go into a break. Well, they're going to get one more stimulus, and then they're going to go into a break phase. And I've instructed my participants that, when they're in a break, feel free to like yawn or stretch or whatever. And so when the participant does that, we can see these. Hopefully this is obvious that this is very terrible. We don't want to see these high frequency bursts of high amplitude noise in our data. And we can also see that the participant does a bunch of blinks as well. So they're blinking a bunch, they're scrunching their face. They're getting comfy because they're going to have to sit through, in total, 30 minutes of this horrible task that I'm making them do. And they're probably getting to the point now where it's like, okay, yeah, this is actually really terrible. I need to take these breaks seriously. Sometimes you'll have subjects that are like, nah, I don't need the breaks. Let's go. But it's like, nope, you have to take the breaks. I'm sorry. So sometimes you know better than your participant about what they need. But yeah, typically I'll show participants, again, I'll show them these artifacts before I start collecting data. So I'll say, okay, blink twice for me. I'll have them look left and look right, and I'll look at the EOGs. And then I'll have them say, okay, be really still for a little bit, and I'll let the traces go nice and smooth. Then I'll say, go ahead and clench your jaws for me. And it just destroys the EEG activity. Once we start collecting EEG data in the lab, when I train the people who want to get trained to collect that, that's going to be the very first thing that we do once the participant that you're working with is capped, is you're going to look for the blinks and you're going to have the person clench their jaws. And I've taken EEGs into classrooms with like high schoolers and middle schoolers and stuff, and they're so excited by the blinks and the jaw stuff. It's ridiculous. It's like they see the raw signals, and it's like, okay, yeah. And then as soon as someone starts blinking, they're like, whoa! And then somebody clenches their jaw, and their minds are just blown. Even though, like, for us, it's just like, okay, yeah, don't do that. But for them, it's like, that's crazy that we can do that, So yeah, the way that we can detect this is by checking for higher frequency noise. Muscle artifacts are actually really easy to just eyeball if you're visually inspecting your data, which all good experimenters should be doing. However, when we're making real-time BCIs, we can't always be visually inspecting the data, right? We're not the ones that are determining in real time, this is good data, this is bad data. We need some automated methods. But when we're analyzing the offline data, or we're doing a pure offline study, we absolutely should always visually inspect all of the data we record. Some people forget this. It doesn't really take that long. You can go through hundreds of participants within a single day once you get good at looking for certain artifacts. But typically we're going to see this again 30 to 100 hertz. And if you wanted an automated method, you could say, okay, if we see a certain amount of power higher than 100 hertz, we can just set a thresholding approach, except within the frequency domain rather than the temporal domain, and just say, okay, 100 hertz power at this level, we call that a muscle artifact, we reject that epoch. So you can do something like that. Typically, we see these muscle artifacts during rests, as we saw in this case. So this is when the participant is taking a break. If you tell your participant to be a good participant, they tend to be good participants. Some electrodes may record higher muscle activity, such as T7, T8, and even the mastoids can record it. And again, you can see these for visual inspection. And sometimes you might want to, anyway, I'm going to skip that point. But yeah, so what can we do for correction? Low pass filtering works really well. So if we want to get rid of our higher frequency noise in 30 to 100 hertz and we don't care about any EEG activity faster than that, then we can just apply a low pass filter, which is why we'll often see a band pass range of 0.1 hertz to 30 hertz when we're looking at ERPs. But again, typically, our actual data does not have these muscle artifacts. We can also drop high muscle activity channels. So certain channels might just be collecting more muscle activity than others, so we don't necessarily have to discard an entire epoch. We can just say, okay, these channels are bad, we're going to drop them. If you wanted to get a little spicy, you could interpolate them, but I wouldn't recommend doing that naively. And then, of course, we could re-reference the data. So certain electrodes record artifacts more readily than others. I'm going to lump in EKG and ECG in this case, even though they're not muscle artifacts, but the mastoids, which we often place behind the subject's ear on the hard bony surface, if you misplace that, or if somebody's vasculature is just in such a way that a vein or an artery lines right up with where you placed your electrode, you will record very clear ECG/EKG. And because of that, if those are your reference electrodes, when you re-reference your data, you're going to see those artifacts on every single channel that you're recording from. So that's obviously a bad idea. And in that case, you might consider using a different reference for that particular subject. So maybe use an electrodes that are close to the mastoids but are not the mastoids, like TP9 and TP10 or TP7, TP8, something like that. And then again, the Hansen's axiom, have participants seated in a comfortable chair to reduce muscle artifacts, back artifacts, have them sit up straight, and then show participants the artifacts just like I was explaining. Yeah.
Can you re-reference the EEG data to, let's say, the eye tracking data? Is that something you can do? Like, if you can measure almost the amplitude, you just take it out by referencing it?
So the question is, can you re-reference the data to the eye channels? So you can re-reference to anything you want. You could, as long as the data are in the same magnitude and they're recorded from the same amplifier, then you can re-reference it safely. So the reason I specify that is because often we're recording EOGs through an aux amp that is pre-amplifying the EOGs. So now we're dealing with signals that are in the millivolts range rather than the microvolts. So you'd have to apply some gain correction to those before you would re-reference. But if you end up re-referencing to a signal like that has noise, it doesn't. I mean, you will cancel out that channel from having that noise because by definition, re-referencing is like getting rid of those channels. But you're now going to be adding that noise systematically to every single channel you're recording. So instead of doing that re-referencing approach, you would try to learn this signature of what these eye blinks look like or eye movements look like, and then use something like a regression-based approach to say, okay, this is the influence of this signal. Here are all my other signals. Let's subtract out the influence from this signal from all the other signals. Does that make sense? But yeah, you're thinking in the right track. It's just don't re-reference, regression instead. Okay, and then other ocular artifacts. So these are not just blinks, they can also be eye movements. They can affect many electrodes just like eye blinks, but they're mostly going to affect the frontal ones. And these are moderately detectable with EOG. It depends on how much the person is moving their eyes. So really large eye movements are pretty easy to detect, but really small ones like microsaccades are nearly impossible to accurately detect if they're really small. And correction can be difficult or it can be impossible depending on the kind of artifact, which I'll talk about. Also, it's becoming clear we're probably not going to be able to talk too much about ICA today, but it's okay. So here's an example from Steve Luck's book about a simple scenario where you have the participant doing these saccades, which a saccade is essentially just an eye movement. I'm going to simplify it. Saccade researchers can yell at me, but if you have a participant who's looking at a fixation cross and then a certain stimulus appears on a screen, the participant will make these small eye adjustments to fixate on that stimulus that's been presented. This might not sound like a big deal, but there are certain tasks such as the like visual search N2PC task where you want the participant to be making their decisions based off of their peripheral movements. So you have the entire stimulus in the foveal range, and because certain things are lateralized, you can't afford to have the user move their eyes and generate artifacts or generate eye movement locked ERPs. So you need to make sure that they're not doing that, and the way to do that is by recording their EOGs. So the HEOGs will produce this very distinct step-like pattern if the user is perfectly moving their eyes left and right. And as you can see, it has this like classic boxcar shape, and you can detect this using a step function, which is shown at the top of the figure. Again, in reality, you tend to record these from symbol voltage thresholding if your signals are really clean, but the step function is a little more deliberate and it can catch smaller amplitude EOG movements. Now the VEOGs look more like regular. They don't quite look like step functions. They look more like peaks and troughs, similar to what you'd see from a blink. It really depends. It's pretty consistent. And when a participant moves their eyes in a way that's diagonal, so not perfectly vertical or horizontal, it'll be sort of a linear combination of these two. And the voltage detected at the electrodes or any given electrode is a linear function of the size, like the amount of eye movement that's generated. And yeah, it can be a problem. They can be easy to detect. And again, this is a scenario where they can be a useful signal. So you can actually use HEOGs and VEOGs and a combination of that to do eye tracking rather than using some video system. They're not as precise as a really well calibrated video system is, but you can do eye tracking with them. So correction. I start with this quote to explain the impossible scenario. So procedures that attempt to correct for the EOG voltages produced by eye movements cannot correct for the saccade-induced ERP responses. So when your eye produces one of these saccades, it's also going to produce ERP components that are locked to that saccade, that are these like visually locked ERP components. And we don't notice anything as our perception system does some filtering. So we don't actually notice our eyes constantly moving and shifting about, but the brain is still generating these responses to these movements. And those ERPs caused by these saccades are not something you can correct with simple processes. It's essentially impossible to fix those unless you systematically record all of these ERP components and you understand them really well and you apply some crazy decomposition thing, like something even gnarlier than ICA, which we're going to end up talking about tomorrow now, or Wednesday, in order to try to separate these saccade-induced ERP responses. But if you're just looking, if you're not trying to fix those components, then you can correct for the actual EOG signals themselves with something like a regression-based approach, or with something like ICA, which would decompose the data, and then you can say, okay, these look like eye movements, let's delete those, and then you'd remix the data. So, but those ERPs, I just wanted to specify that those ERP components that are induced by the saccades cannot easily be corrected. And this actually opens the door to, I don't want to talk too much about this, but you can synchronize ERPs to the onset of certain stimuli or a response, which is very common, but you could also look at ERPs locked to when participants move their eyes and look to certain events. So this could be particularly interesting if you're studying something that is very dynamic. So I'm interested in, for example, studying naturalistic tasks like video games. And as you can imagine, there's so many events happening and so many things on screen for a complicated game like StarCraft or something that it would be unrealistic to use standard event synchronization to see what activity is happening at certain events. Rather, you'd want some labeling approach that is working in concert with some eye tracking based approach that knows, okay, a participant has looked at this stimulus at this time, that's when I want to look at the EEG data, not I got this event, because that's not necessarily when a participant has actually foveated to a stimulus, if that makes sense. So again, it's a scenario where some of these things are artifacts sometimes, but they can be useful signals if you design your experiment in such a way to utilize them or depend on them. Cool. And then the Hansen's axiom, again, show participants these movements, instruct them that they need to fixate on the center of the screen if they need to fixate on the center of the screen. And that's about it for for ocular artifacts. Otherwise, yeah, you just need to make sure you're recording EOGs and make sure that certain artifacts are not being generated if your task depends on it. Okay? And then the final set of things I'll talk about are environmental noises and skin potential changes. These are the things that you sort of can't do anything about for the most part. They are just constantly around us. So the most common environmental noise is line noise. So all of these lights and all of our electronics are plugged into, at least in the US, 60 hertz alternating current. And if you have a poorly shielded room or poorly shielded amplifier or poorly shielded electrodes, you can just see this really high 60 hertz activity in your signals. It's very obvious. It's the most common high frequency noise you'll see, and it's easy to deal with. We can just filter it out if we're recording from good equipment. So for example, when you're recording from an expensive amplifier like my Brain Vision AccuChamp and you have active electrodes, you see pretty much no line noise at all. But when we're recording from our passive electrodes with the ActiChamp, or sorry, with the OpenBCI Cyton, which we will be doing, you're more likely to see an influence in the 60 hertz noise. And the easiest way to mitigate that, if you have no control over your environment, which sometimes we don't with these portable systems, is we just apply a notch filter, or we just apply a pretty aggressive low-pass filter after, let's say, 30 hertz, or a combination. We can mitigate the effects of the AC-powered lights by turning on a battery-powered light during data collection, or in some experiments, you just turn a light off. It really depends on the context. You want to be careful with using low light or no lights because it will make participants fall asleep. That happens a lot. They don't quite fall all the way asleep, but you can see them getting drowsy, and you have to correct for that. Sometimes that's when you, like maybe you have a policy where you want to do lights off first, but then it's like, okay, we really need, like it's worth risking some 60 hertz noise to be able to collect data, so then you turn the lights back on. You can also mitigate that with a shielded room or active electrodes and shorter wires. So the longer that your wire gets, the more it acts like an antenna for picking up all sorts of EM noise in the environment. So having pretty short leads will help a lot. Actually, there's a bit of a debate, or quite a debate, depending on who you talk to, about whether or not active electrodes are even worth anything. There are a lot of experimenters that just are like, nope, all you need is a clean recording condition, and passive electrodes and short wires are all you need. But if you're trying to record in noisier environments like a workplace or a hospital or something that just has electrical noise, like a forest has trees, then you're going to need to think a little more carefully about shielding and active electricity or active electrodes. And then skin potential changes. Sweat is the biggest one, so this is just going to happen while the participant is just existing as a human being. This can be mitigated by having a relatively cold room. Typically, we'd record at 68 degrees at my old lab, and that does reduce some sweating artifacts. Oftentimes, it's not going to be a huge problem because we can high-pass filter the data at 0.1 hertz to remove these really slow drifts. And again, these are one of the variations that tends to be quite random, and it exists across the entirety of your recording, so across all of your conditions. So they tend to average out and not be a real problem. So it can be a problem if you're doing single trial and oscillation-based stuff, if you get this low power spike, but most of the time it's not a huge deal. I also wanted to highlight an interesting artifact, which is the tongue movement. So the tongue is also a dipole. So if you just have your mouth closed and you just move your tongue up and down, it can completely destroy the EEG data. So if you ever need a polygraph for some reason, just move your tongue a bunch and you'll get away with it. But okay, I'll talk some more about artifacts and ICA at the start of next class's lecture. And in the meantime, feel free to come to office hours and ask questions on Piazza and such, and start thinking about your final projects, which I'll post more about probably today.